Dear students, today we'll see what is sampling theory. Now in sampling theory, an analog signal, a message signal or information signal is converted into its samples. That is, a continuous time signal is converted into discrete signal, where you have number of samples what you get at the output. And those number of samples depend upon the frequency of the analog signal. Okay, for example, if you see, this is your sampling, this is your analog signal. Okay, this is your analog signal, this is amplitude, and this is time. So this is your analog signal xt. Now this can be converted into samples like this. If you see that, you can have the same type of envelope. This can be the first sample, this can be the second sample, this can be the third sample, this can be the fourth sample. So this is also amplitude versus time. So this is your first sample, second sample, third sample, and fourth sample. And there will be a specific time period between the sample, which will be called as TS. This will be called as TS. This is the time period between samples. Now, always what we do, we will convert analog signal into samples in a process of analog to digital. So, continuous time is converted into a discrete time. And this discrete time signal is further again quantized, encoded, and it is sent for transmission. And whenever you receive it, the number of samples what you are having matters. The number of samples should be so many that you are able to recover the original signal back. This is the original signal. You should be able to reconstruct the original signal back from the samples. And that is why some sampling theory becomes important. The number of samples what you have depend on what is the frequency of this analog signal. Say for example, this analog signal is from 0 to 5 kilohertz. Then the maximum frequency is 5 kilohertz of this analog signal. That 5 kilohertz will decide the sampling frequency, that is how many number of samples can come per second. Sampling frequency is given as, if this is Ts, sampling frequency Fs is equal to 1 upon Ts. So sampling frequency is given as 1 upon Ts, and then sampling frequency depends upon the highest frequency of the modulating signal, of the analog signal, of the message signal. So this becomes important, and therefore we can decide how many samples we can get. And depending on how many samples we are getting, we are able to know that whether we can reconstruct the original signal back at the receiver part. So this is what you have to keep in mind before we go to see what do we mean by sampling theorem. Now students, to know what is sampling theorem, we have to consider first an analog signal. This will be your analog signal xt, which will be your information signal or message signal, anything you can call it as. It is a continuous time signal. And second, what you have to take is a train of pulses. You should have a train of pulses. Now these pulses will have constant amplitude, constant pulse width, and constant position. Constant amplitude, constant pulse width, and constant position. Okay. Now, to get the samples of this analog signal, we have to multiply these two. That is the analog signal xt and the train of pulses st. We have to give to a multiplier. So there is a multiplier. One input will be xt, that is this analog signal. The other input is train of pulses, that is st. And the output will be st into xt, that is product of that. And when you see the product of that, for example, here we have shown pulse amplitude modulation. So all these pulses will take the amplitude of this instantaneous value. Now this pulse which was there will take this amplitude and it is shown here. This pulse will take this amplitude and it is shown here. This pulse will take this amplitude and it is shown here. This pulse will take this amplitude and it is shown here. So you can see this amplitude over here is shown here. So whatever amplitude you have here, same amplitude you have here. Similarly here, if you see, this amplitude will be here. Similarly here you will see this amplitude will be here. So in that way, all these pulses have taken the amplitude value of the instantaneous. That means this signal, this analog signal, this continuous time signal is converted into samples, discrete samples here. Now this is what is your making of samples. Now in this making of samples, you have maintained a time period Ts between every sample. Now the Ts will give you the frequency of sampling. Frequency of sampling, that is how many samples per second. So that frequency of sampling Fs is equal to 1 upon Ts. 1 upon Ts. Now how much should be that frequency of sampling? How many samples should come per second? That is an important question. Now that will depend upon what is the maximum frequency of this input analog signal. Now this input analog signal will be from 0 to 1 kHz, 0 to 2 kHz, 0 to 3 kHz, 0 to 5 kHz, anything. So we can take it as 0 to maximum frequencies FM. Maximum frequencies FM of this signal, your information signal. Maximum frequencies FM. Then according to our sampling theorem, what it says that you have to make so many samples, you have to construct so many samples. The number of samples per second should be such that the sampling frequencies should be such that it should be twice the highest modulating frequency, that is FM. Twice the highest modulating frequency, at least twice or more than twice. More than twice or at least twice the highest modulating frequency, so that you can reconstruct the original signal at the receiver from these samples. Understood? It says that your sampling frequency Fs should be greater than or equal to twice Fm. Your sampling frequency should be greater than or equal to twice Fm. That means number of samples per second should be so many that it should be twice, at least twice or more than twice. So it should be twice the highest modulating frequency of the information wave of the modulating signal. Here the modulating signal highest frequency was 0 to FM. So FM is the highest frequency. So sampling frequency will be greater than or equal to twice the highest modulating frequency. That is, Fs is greater than or equal to 2FM, so that if you maintain this, you can reconstruct the original signal at the receiver from these samples, because the receiver will get these samples, and from these samples you have to get the signal. So to do that properly, you have to maintain this. This is what your sampling theorem says. Sampling theorem says that if you are having a signal from 0 to FM hertz, okay, and if you convert them into samples, then the sampling frequencies should be such that sampling frequency should be greater than or equal to twice the highest modulating frequency Fm, so that you can reconstruct the original signal back at the receiver from its samples. This is what your sampling theorem says. Now this is very important. Now here we are saying Fs is greater than or equal to 2Fm. If you take the basic condition where Fs is equal to 2Fm, this basic condition is called as Nyquist condition or Nyquist criteria. Okay, Fs, that is sampling frequency, is equal to twice the highest modulating frequency, is also called as Nyquist criteria or Nyquist a condition. Clear? So this is what your sampling theorem says. And now students, we will see sampling of low pass signals. Now in that case, first we have to consider what is our signal in time domain. So this is our signal shown xt. So this is what is the analog signal shown as xt in time domain. That is with respect to time, it is shown like this. Okay. Now the same signal, if you put it in frequency domain, the same signal if you put it in frequency domain, it will look like this. This is for frequency and the x-axis is for frequency. This is your frequency domain. Now here we know that our frequency of analog signal was 0 to FM. The highest modulating frequency was FM. And if you put it in frequency domain, you can see that from 0 you are going to plus FM here and minus FM here. So this is your frequency domain diagram for the analog signal. So this is 0 to FM on the positive side and 0 to minus FM on the negative side. So this will be your frequency spectrum for this signal. This is in frequency domain, this is in time domain. So in time domain you can see the signal like this, in frequency domain you can see it like this. Now for our sampled wave, we have to multiply our signal by the train of pulses as we have seen in our sampling theorem. This signal has to be multiplied by train of pulses. This is train of pulses shown, that is on the basis of time. Signal st is shown and the first pulse is at time ts, second pulse is at time 2 ts, third pulse is at time 3 ts, 4 ts, 5 ts, and you can also have it on the negative side, minus ts, minus 2 ts, all you can have, and all this train of pulses will be multiplied by your original signal. So the analog signal, the information signal will be multiplied by your pulses so that you can get a sampled wave output based on this analog signal. Now the mathematical equation for this train of pulses is given like this. St is equal to 1 upon ts, 1 plus 2 cos omega st plus 2 cos 2 omega st plus 2 cos 3 omega st plus 2 cos 4 omega st plus 2 cos 5 omega st dot dot dot, it will go on. So this is a mathematical equation in time domain for your train of pulses. Now this equation should be multiplied by xt, that is your analog signal, time domain, and then you will get a product for time domain. That product should be converted into frequency domain, and for that frequency domain product, whatever series you get, for that you can draw a spectrum, and in that spectrum you can tell how you can do sampling of low pass signal. Okay, now we will do the next, that we will multiply the train of pulses equation by xt and see what product we will get. And now students, if you see the product of analog signal xt multiplied by train of pulses st, then you will see xt multiplied by 1 upon ts, 1 plus 2 cos omega st plus 2 cos 2 omega st plus 2 cos 3 omega st plus dot dot dot. If you put this into frequency domain, that is your frequency domain analog signal multiplied by train of pulses will give you 1 upon ts x omega, okay, plus x into omega minus omega s plus x into omega plus omega s plus x into omega minus 2 omega s plus x into omega plus 2 omega s plus x into omega minus 3 omega s plus x into omega plus 3 omega s dot dot dot, this will go on. Now this, in place of omega you can take f also, you can take frequency or you can take angular frequency. Either you can take f or you can take 2 pi f. So omega is equal to 2 pi f. Now here if you see, you are getting this first term as the signal itself. The first term is signal itself. And the second term, if you see, it is a double sideband at a frequency omega s or fs. If you see the third term, it is at 2 omega s or 2 fs. If you see the fourth term, it is centered at 3 omega s or 3 fs. So these are double sidebands which are projected on either side of the spectrum. And in the center of the spectrum, you are having the signal itself. So this is what we have to first draw. And after drawing that, you can understand what we are going to actually low pass. And what do you mean by sampling of low pass signals? Now here students, if you see the spectrum of the signal and the sampled signal. So here in the first figure we have shown spectrum of the signal. So we have seen that it will go till plus FM and minus FM. So this will be a spectrum of the original signal, that is XT, which was converted into frequency domain. Now this is a spectrum of ST into XT, that multiplied product what we got in frequency domain. We can show the spectrum like this. This is your original signal, which is from 0 to FM till minus FM. This will be the double sideband which is centered at Fs. This will be the double sideband which is centered at minus Fs. This will be double sideband which is centered at 2Fs. This will be double sideband which is centered at minus 2Fs. Now, if this sampled signal what you get at the receiver, if you pass it through a low pass filter, who is having cutoff frequency FM, the low pass filter is having cutoff frequency FM. That means it will pass all the signals from 0 to FM. So 0 to FM, all the signals are passed. That means it is going to pass this part of your spectrum 0 to FM. Now we know that in a double sideband where it is 0 to FM and 0 to minus FM, the information in this part, that is upper side, will be same as information in the lower side. So we want one part of it. So one part of it if you want, then you can have 0 to FM. And for that you can use a low pass filter. So if you send the signal through a low pass filter, then that low pass filter will pass only 0 to FM, the information which was duplicated here. So one part of it, that is the upper side, we have taken 0 to FM will be passed, and rest all will be blocked. Rest all frequency will be avoided. It will be rejected. So you are going to pass only 0 to FM, and hence we can recover the original signal back. We can get the original signal back by a low pass filter. So this is called as sampling of low pass signals. Now here students, we'll see sampling of band pass signals. Now here in the first figure, we have shown the frequency domain spectrum of your information wave or the message signal or the analog signal. And this message signal does not have a frequency from 0. It is having frequency somewhere in between. So here you can see it is having frequency from 2Fs to 2.5Fs, and on the negative side you can see it is having frequency from minus 2Fs to minus 2.5Fs. Now this signal, if you multiply by train of pulses, and if you get a sampled wave, and that sampled wave if you put it in frequency domain, you will get something like this. From 0, then Fs, 2Fs, 3Fs, all these are centered frequency where you can have a double sideband, and on the negative side you can have minus Fs, minus 2Fs, minus 3Fs. Here also you are having centered frequency and you are having a double sideband. Now from this sampled wave, we want this information back, because our information lies from 2Fs to 2.5Fs, that is 2Fs to 2.5Fs. This part I want to take out because that is my information signal. Now to have this part out, I should use a band pass filter. A band pass filter which is having cutoff frequency 2Fs and 2.5Fs. That band pass frequency, band pass filter will pass only this frequency and it will block all other frequency. And if you are able to recover this frequency back, if you are able to recover this, then you are able to recover your information back. You are getting your information back. So this is what you can study in sampling of band pass signal.